Okay, hello everyone. I'm Fei. I'm a HPC technical consultant from SHARCNet. Today I'm gonna deliver a webinar called CUDA Profiling and Tuning. So in this webinar, I will briefly talking about some CUDA review and I give you some idea behind the GPU profiling and optimization. And I will also cover how to use Nsight or Nvidia Visual Profiler on SHARCNet machines. And the very important thing I want to introduce to you is the performance limiter, the warp, and the occupancy. After this, I will also introduce some hardware background, including the instruction latencies and throughput. And after you got all this background knowledge, and then we can play with some shuffle instruction and the instruction-level parallelism to say how we can do to improve our performance on the GPU. Okay, so let's move to the first thing. It's the CUDA review, and CUDA is the programming model used on Nvidia GPU. So there are two basic things you should know about is the thread and blocks. So each CUDA program will have multiple blocks in a grid. But for each block, there are multiple threads that you can control to do some calculation. The memory hierarchy is very simple. There are mainly three different levels. The first one is the largest one is global memory. Usually it can be a few gigabytes large. And the speed of the global memory is around 100 to 200, maybe more gigabytes per second. It's not that as fast as other memory on chip. The global memory is shared by all the device. That means all your program, no matter if it's the same kernel or not, all your thread, all your blocks can see the global memory. And there is also a shared memory area. So in the shared memory area, only the threads within the same block can access the shared memory. So that's the reason why they call it shared memory. It's shared by all the threads within the same block. Shared memory has a much higher memory bandwidth. It can achieve around 1 to 2 terabytes per second, depending on which hardware architecture you have. And we also have the fastest one storage place is called a register. Register can easily achieve like 7 terabytes per second bandwidth, but it's only visible for each thread. Well, it's not actually only visible for one thread, but for the programmer, it's only visible for the threads. But for the hardware, it can be shared to other threads. I will talk about it more later. Okay, the basic code flow of CUDA is the heterogeneous programming model. So for example, if we execute a sequential C program, then we have one or multiple threads as in our host code. Then one thread in the host code can execute the kernel on the device. It can also prepare the data and copy the data from host memory to the device memory, then execute the kernels on the device. And after the device finishes the calculation, and you can also use the host thread to copy the data from device back to the host memory and do some other things. Then you execute or launch other kernels. Okay, so the GPU profiling and optimization. The first question I want to ask is, why do I need to profile my code? Well, the reason why behind the profiling the code is that you want to know how fast your program can run, or you want to know if your program runs fast enough or not. So let's take a look at this picture here, and we can find for different generation GPUs has different capability of doing the computing. they have different performance indicator here. So for example, if we have a code written years ago, maybe it was optimized by some old architecture like GeForce 800. But what if we run this code on our newest architecture, like GeForce 780 Ti? What will happen? It may not run very fast on the newer GPU. That's a reason why they need to profile your code again to say, okay, if my code ran fast enough on the certain architecture. So the optimization goal is very simple, is to fully utilize all the hardware resource. If you want to run a code very fast, and you should use all the hardware resource on the GPU. Not only the computing unit, but also the memory controller, that everything on the GPU, every hardware on it is available for you to use, and you'd better use all of them. All right, to profile a CUDA program, the best tool you can use is Nsight and NVVP from Nvidia. So Nsight is a fully featured IDE. Nsight has two versions. One is Visual Studio version for Windows machine, and another one is the Eclipse version for the Linux and the Mac. Today I'm going to use the Linux version as an example to show you how to use the Nsight on SHARCNet machine. So by using the Nsight, you can easily editing your code, building your code, running your code, or debugging and profiling your code. So what is NVVP? NVVP is Nvidia Visual Profiler. Well, before Nvidia built the Nsight, Nvidia supplied the NVVP at that time. So NVVP is a profiling tool, but nowadays that Nvidia integrate NVVP into the Nsight, so you need Nsight only, you don't need a separate NVVP. For example, if you want to profile not a CUDA program, but an OpenCL program, you may need the NVVP to run independently. Okay, so using Nsight on SHARCNet has two ways. The first way is use the development nodes on Monk or any other contributed cluster that has development nodes. And you can use the SSH to the development nodes and use the X11 window forwarding to open a window that you can see the Nsight. I will show you how to do that later. But you have to notice that the GPUs on Monk is relatively old, is Fermi based, so it may miss some function. And I would suggest you to use the newer GPU. We got a cluster Andrew. Even Andrew is an old cluster, but we upgrade some Maxwell GPU on it. But there isn't any development node there, so you have to submit an interactive job, and then you SSH to that node to open the Nsight. Okay, if you don't know how to submit the interactive job, just reference our help wiki. There is a very detailed instruction on how to do this. Okay, let me switch to the terminal and show you how to use the Nsight on SHARCNet. Alright, you can just choose Monk as an example to see how to do that. But before you SSH to Monk, you have to remember that to put a -y flag before you SSH. That will enable you the X11 forwarding. If you are using Mobile Xterm or other tools on Windows, please check the configuration to make sure that is the X11 window forwarding has been enabled. Okay, after SSH to Monk, we SSH to the development node 154. So please make sure that to check the version of the CUDA, because Nsight, different version of Nsight comes with the different version of CUDA. if you want to use the newer Nsight, you have to use the newer CUDA. For example, we use the CUDA 6.0.37 here. Once you loaded the CUDA modular, and you can find the Nsight on the default path. So you just say Nsight. Then we open a window. Alright, so after you're running the Nsight, you will see IDE here. If you're familiar with Eclipse, you will see, okay, this is exactly like the same as the Eclipse IDE on the Linux. Okay, let me switch to another cluster. Okay, but today I'm not going to use Monk as an example to show you how to use the Nsight. I'm going to use a new contributed cluster called Mosaic that has a newer K20 GPU to show you how to use the Nsight. So let me switch to the Mosaic. Okay. So Mosaic has the developer node almost one. But you have to notice that the Mosaic has a problem because the Linux kernel has some conflicts with the Eclipse, a certain version that provided by CUDA 6.5. So if you want to use CUDA 6.5, you have to modify some files. But I have already modified some files here under my. Okay, I copied all the Nsight into my folder and modified some settings so that it can be run on Mosaic. If you want to run it, you just submit a ticket or send an email to help@sharcnet.ca, and then I will show you how to do that. Okay, it's the same thing. After switching the modular to the CUDA 6.5, and we can run the Nsight on this new cluster. Okay, when you open the Nsight, you can have the Project Explorer here, and you have your source code displayed in the front. It's basically the Eclipse thing. If you don't know how to use Eclipse, you just Google the internet and you will know how to do that. And there are some buttons here that you can just easily just create a CUDA project here. It will set up all the environment setting, compiler setting for you. It's very easy to use. Today I'm not going to show you how to use this, but I want to show you how to use it for profiling. Okay, I assume that you have all the code ready here, and you have already built your code. Then you can see there was a little button here called Profile. You click it, and it will start to profile the code. Give the program some time to do. Okay, so once you click the profile, the program will run in the profiling mode, and it will generate this graph in the middle. Then you can see, okay, let me zoom it a little bit. Okay, you can see there are different function calls from the host, and there are two kernels for the GPU device. And in my code, I just ran the kernel 5 times, so you will see that on the timeline there are 5 kernels execution here. Each kernel takes very small amount of time. So once you click each kernel, you will see some details on the right side. So the start time, then the duration, and you can also see the grid size, the block size, and some very basic information. If you need to know, okay, I want to profile my kernel in detail, you just click one kernel, and then you say on the left bottom corner, there were some options for you to choose. At the bottom, there was a button say switch to ungated analysis. Okay, let me make it bigger. So you will see you have different things you can know. Let's just click the analysis all to see all the information that collected by the profiler. Okay. It will run the program twice to get a detail. Okay, so on the right side, you get some results. It's very basic tips to show you there might be some performance problem for your program. And you have the detailed profiling result on the left. So for example, we clicked one, this is called the kernel performance limiter, and you got kernel latency, you got kernel compute, a lot of things. So if you took a look at the area on the right, you will see, okay, we got more details here, like a shared efficiency and global efficiency shown as none. But you got warp execution efficiency. You got more details once you analysis for the kernel. Okay, so now let's go one by one from the kernel performance limiter. So the kernel performance limiter is the most important thing you should know about your program. It will show you the potential bound, the potential problem from your program. Okay, you can take a look at this. This graph shows you the utilization of different things on the GPU. On the left side, there was a compute utilization. On the other hand, there was a memory, because the compute unit and the memory controller are separate, so the information can be collected differently on different parts. So this program shows very low memory utilization, and it shows not less than 60% of compute utilization. So the Nsight will also give you some conclusion or some guess about what's going on with your problem. So you will see that kernel performance is bound by instruction and memory latency. So it's not bound by the memory bandwidth or the compute unit. It's bound by the latency, because both compute and memory utilization is below 60%. Okay, let me give you more detail about the performance limiter on the slide. Okay, so the performance limiter is something we use to tell if the code is compute or memory bound, or if latency bound. So look at this graph. So a typical compute bound program will show a high compute utilization, but relatively lower memory utilization. A typical memory bandwidth bound will show the opposite, will show relatively higher memory bandwidth utilization. If both compute utilization and memory utilization are below 60%, then Nsight will consider this program as a latency bound. If you achieve both compute unit and the memory unit a high utilization, that means your program is compute and memory bound. But this graph is only from the hardware side. It's not from the nature of the algorithm. Because if you got a latency bound like this, it doesn't mean your program is, even you have a higher memory utilization, but it doesn't mean your program is memory bound. Sometimes, just like what we saw before, just remember that we saw the graph before I switched to the slides. The compute utilization is higher than the memory utilization, but actually my code is a memory bound. It's not a compute bound, even it shows a higher compute utilization. this performance limiter is something the hardware tells. It's not the real nature of your algorithm. Okay, so you see that my program shows the higher compute utilization than the memory utilization, but it doesn't mean that my program is compute bound. Actually, my program is memory bound program. The reason why I got this is because both utilization are below 60, so it's not compute bound or memory bound. Now the program is a latency bound. Okay, let's move to the kernel latency part. All right, so here is a graph showing that the kernel latency. There are a lot of detailed instructions on which latency is and what's the stories behind them. You can take a detailed look at that later. But the first thing I want to show you is the occupancy here. So there is a graph shows the occupancy. If you learn CUDA in the earlier time, you will remember that there is an Excel file in the CUDA that help you to calculate the occupancy. But now you can use the Nsight to calculate automatically. So Nsight will generate the occupancy information about your program. Okay, to get a better understanding of the occupancy, you have to know what is a warp. So a lot of programmers think that the thread is the smallest unit that you can control in CUDA. That is true because thread is the smallest unit that you can control by the programmer, but thread is not the smallest unit that can control by the hardware. So hardware to hardware, a warp is the smallest unit that can be scheduled, that can be issued, that can be executed on the multiprocessor. A warp is a bunch of 32 threads. It's a 32 continuous thread that can run physically on the multiprocessor. It looks like an SIMD things. In this, we have single instruction, multiple data, but we have 32 data, so it's called a warp. It's a kind of SMD things. Okay, so the occupancy is the active warps divided by the maximum active warps. So the maximum active warps is limited by the hardware. Different hardware will have the different limitation on the maximum active warps. So the active warps, the occupancy is how many warps that can be run active, how many active warps that can be run on the hardware. So there are some occupancy limiter. So the first thing is a register. Register is the limited resource on the graphic card. It's very valuable, and there are only 64 kilobytes register per each multiprocessor, and there are some limitation for the number of register that can be used by each thread. Different hardware will have different limitation. For some kind of hardware, will limit one thread can only use 255 register. And another thing is shared memory. Shared memory is another limited resource on the multiprocessor. So if you used up all the shared memory, you're not able to run more warps on the multiprocessor. Another thing is block size. So if you have a very small block size, for example 32, is 1 warp per block, but the number of blocks is limited by some other reason. If some other reason you limited your block, or the hardware will limited your block to 8, then you can run only 8 blocks on this multiprocessor. Then it will limit the occupancy because each block has only 1 warp. That means in total you have only 8 warps. But the maximum active warps will be 64 for the Kepler architecture. So you can only achieve 1 out of 8 occupancy. The thing I want to mention here is 100% occupancy isn't needed to reach the maximum performance. Once the needed occupancy is reached, further increases won't improve any performance. A lot of people believe that 66% occupancy is enough for most programs. If your program has more independent work per thread, then less occupancy is needed because you have more instruction to issue. You get more, even you have a small amount of warps, but each warp has a lot of instruction that it can overlap between together. And I will show you the detail later. So if your program is memory bounded code, that probably you need more occupancy because if your program is memory bound, for each warp there are less instructions. And the memory load and store instruction usually have higher latency, so you need more work to hide this. So sometimes increasing the occupancy for the memory bound problem will increase the performance. Okay, so the next thing I want to show you is the instruction latency and the throughput. It's very important concept based on the things hardware you should know. Okay, let me open the graphic here. Alright, so this graph shows you the stream multiprocessor. It's called SM. The left one is from Kepler architecture and the right one is from Maxwell. So maybe you cannot see it clearly, but let me show you. There are 4 different units you can see in different colors here. So the green little one is the core. That is for the single position floating point. And you can also see there is a dark green one on the left. Is the LD&ST unit. It's a load and store unit. This unit are used for loading the data and storing the data. And in the Kepler architecture, there are also some double position units, and you also have some special function unit for solve the sine functions like sine, cosine. The Maxwell architecture is quite similar, and you also have this unit, but this doesn't have the double position unit showing in this graph. Okay, you can see there are 4 schedulers here on the top of the Kepler architecture, or there are also 4 schedulers in the Maxwell, but these 4 are separate. Each scheduler can issue 2 instructions at a time to the pipelines. And there are different kind of pipelines, the load and store pipelines, the arithmetic pipelines, the control flow pipeline, and the textual pipeline. Okay, let me draw something to show you how each instruction issued and executed on the hardware. Okay, so for example, we have some instruction here. So the instruction going to the instruction cache. And each warp scheduler looking to the cache to pick up some instruction to schedule. Each warp can pick up 2 instructions to issue. So that is called a duty issue. Then the warp scheduler issue these 2 instructions to different pipelines. For example, if we want to load something from shared memory, it will go through the load LD and ST pipeline here. So they pick up some load and ST storage unit to run. During the same time, the scheduler can issue another instruction to another pipeline that is a variable pipeline. For example, they can go to a arithmetic pipeline here to do some calculation. For example, adding to number. But this, the core, each core can only access the register file from this here. So we'll pick up two number from the register and then sum them together and put them back. If you want to save this number to a shared memory or other place, you have to use the LD and ST unit to share them. Otherwise, each core can only access the register files. Okay, there were also some textual files and the other things here, but it's not quite important to concept to understand our topic today. So the difference between the Kepler and Maxwell is that each scheduler can only schedule the instruction to the certain part of the string multiprocessor. So that's the difference. So we have 4 schedulers in the string multiprocessor. That means at the same time it can issue 8 instructions to pipelines. But it's not true. Theoretically it's 8, but it can achieve only 7 instructions. I mean, consistent 7 instructions at a time. Once you know how this instruction issued and executed on the hardware, you should take a look at this graphic to find out what kind of latency is the problem of your program. Okay, so if you take a look at this picture, you will see the instruction stalls has some reasons. The biggest reason is the execution dependency. And another reason is the synchronization. Okay, yes. And you can also get some information about the utilization for each multiprocessor. Okay, I'll talk more about this. If your program has only small data to process, that you may not achieve the highest multiprocessor utilization. So just make sure that you have enough work to do to achieve the highest utilization. Okay, let's switch to the kernel compute. The kernel compute page will show you how busy each pipeline is, or it calculates how many instructions are issued into different pipelines. So the first graph is function unit utilization. As I told you before, there are 4 groups of pipeline: low storage, arithmetic, control flow, and textual. This graph shows very low utilization for each pipeline, groups of pipeline. So that means our program is not quite efficient at all. So you got some other things about the instructions, about the floating number operations. Okay, if you take a look at the kernel memory page, you will see, okay, my program is memory bounded, so I want to achieve the highest memory bandwidth on this hardware. But unfortunately, I can only achieve this 45.9 gigabytes per second is far behind the maximum value is around 200. So that means my program isn't quite efficient on this kind of hardware. All right, once we know the hardware knowledge, we can move to solve the real problem we have today. So I used the example code used in the summer school. So it's a binary reduction code. It's very easy and simple. And you load 2 data to the shared memory, synchronize all the warps in the block, and then you reduce to half-size data, synchronize again. Then you reduce to another half the data until you reduce the data to to one element. It's very easy. Then you can find this graph on the internet from the Nvidia. It's very easy things. Today we don't focus on the memory. We focused on the instruction. So the instruction latency for this program has two problems. One is execution dependency, as we saw. Execution dependency means that for each warp, if you want to execute one instruction, but the instruction cannot be executed because it requires some data that is not available. So the instruction stalls there to waiting for the input. And another problem is the synchronization, because we have to load all the data into the shared memory, then synchronize them, and then we can execute them. So the warp is blocked by a single thread calls. Okay, so I think you are more familiar with the synchronization, so let's start with the synchronization part. So we can do something to reduce the synchronization latency by using the shuffle instruction instead of a shared memory. Previously, we put all the data into the shared memory because shared memory is the only place that we know before that can be used to communicate between each thread, but there was some shuffle instruction that can be used to do the same thing. I will introduce you later. And for executing dependency problem, and we introduced the instruction-level parallelism. Okay, so the shuffle instructions. The shuffle instructions is hardware instructions that can be used by each thread to read a register from another thread. But there is a limitation here. Is the shuffle instruction only works within the same warp. That means you can only use shuffle instruction within the continuous 32 threads. Okay, and it's only supported on compute capability 3.0 and higher. That's the reason why I choose to use the K20 GPU instead of the GPUs on the Monk, because Monk doesn't support the shuffle instruction. Okay, this is the very basic example of how to use the shuffle instruction to do the reduction. So you can see here, for example, we have 8 elements in the warp. It doesn't matter, just assume we have 8 threads in a warp. So you can do a shuffle down, means to get some value from some offset. If the offset is 4, the shuffle down function will return a value that has the offset of 4. The distance of 4. And after that, we can sum them together. And after we sum them together, we can use another shuffle instruction to get the value that has the distance of 2. And after that, we have the distance of 1. Then we put this into the loop, and we can get the final result. After we get the final reduction result from a warp, and we save the result to the shared memory, because we want to share this data between warps, and there is a shared memory, the only way that can share the data between warps. Shuffle only works within the warp, it doesn't work between warps, so you need the shared memory to save the warp. And after that, we execute another warp and to do the calculation until we get the final result. Okay, let's switch to the shuffle code. All right, once we build this code, we can just click the profile button, and it will run the profiler. If we want to have a detail about the kernel, we clicked one kernel, and then we switch to unguided analysis, and we click the analysis all. Okay, so after using shuffle instruction, So we can see here, the memory unit utilization improves a lot because we don't face the synchronization issues here. So more thread can be executed to load data from the memory controller. But the compute part is still low because the nature of our program is a memory-bound program. It loads 2 data and only calculates once. Okay, so if we take a look at the kernel latency here, you will see the synchronization is not a problem at all anymore. So the problem we have now is the execution dependency. If you take a look at the instruction of execution dependency, you will see some words here. Execution dependency. I'm not quite sure if you follow me to this. The execution dependencies and input required by instruction is not yet available. So execution dependency stalls can potentially be reduced by increasing instruction-level parallelism. Okay, the Nvidia suggests us to put more instruction-level parallelism here. Then we follow the instruction from Nvidia and try. Okay, let me switch to, so what is instruction-level parallelism? I believe that you know the thread-level parallelism is what CUDA is. CUDA programming model is the thread-level parallelism. That means more concurrent threads can be executed. The instruction-level parallelism means more concurrent instruction. That means instructions themselves can overlap to each other. So the reason why we can overlap instruction is because every instruction we execute has some latency. When we issue an instruction, it will not return the result immediately. They have some latencies. For arithmetic instruction, usually we have 20 cycles latency. That means if you issue an instruction to say, okay, calculate the summary of 2 elements, and you have to wait 20 cycles until you get the result. If you want to read something from the shared memory or the L1 cache, it takes 20 to 40 cycles. Well, if you want to read something from global memory, that it give you, you need 400 to 600 cycles. The GPUs use switching warp to hide the latency. That means once you issue a memory load instruction, load a memory from a global memory. After issuing this instruction, the GPU will switch to another warp with another independent instruction, and then issue that instruction. After 400, 600 cycles, then it will go back to this, switch back to this, the previous loading instruction, and get the result. So it's different from how CPU hides the instruction latency here. So for our reduction problem, we want to hide more addition instruction into the load instruction because obviously load instruction takes longer time to execute. So we need more addition. But due to the nature of our program, we cannot have more operations. But what we can do, we don't have to put more operations to increase the more instructions. We just want more instruction that can be issued or that can be scheduled on the warp, not on the warp, on the stream multiprocessor. There was some limitation of number of instructions that can be scheduled on the multiprocessor. It's limited by the first thing is number of active warps. Only the active warps, only the instruction from an active warp can be scheduled on the multiprocessor. Even you can have a lot of warps, you have a lot of threads, blocks, warps, but if the warp is not active, you cannot issue the instruction inside that. So the GPU can only switch warps between active warps. It cannot switch a warp to inactive warps. So another thing is you want to, if you got the 100% occupancy, that means you reach the limitation of number of active warps. Another thing you can do is increase the number of instructions in each warps. So that is called instruction-level parallelism, because we bring more instruction to the scheduler, and then the scheduler can switch between warps between different independent instructions to hide the latencies. Okay, so for our reduction problem, we increase the number of instructions within the thread, or within the warp actually, but for programmer, we increase the instruction within the warp. We can do like this. We use previously one thread load one element to shared memory or use the shuffle, it doesn't matter, but one thread only calculates two elements, a pair of elements. But what we have to do now to increase the instruction-level parallelism is to add more elements before the binary reduction. That means we do a serial reduction before the binary reduction for each thread. Each thread loads multiple pairs of elements and calculate them together and store them to a register. You remember that I mentioned register is the fastest memory that we can use, so it will be very fast to store that into a register, not into a shared memory. So we can use the register here because it's only one thread. This one thread, we don't have to share this result with other thread. This is only for one thread, so we can use the register instead of shared memory. And after we store some temporal result into the register, we sum them up, and then we use the shuffle instruction to sum them between threads. Okay, so I have to do some little modifications here. For example, we do 16. We sum 16 values before we do the binary reduction. So it's very easy. We just find out where we go to the binary reduction. We just do like this. Okay, we have one register T1 and some 2 value, and we got T2 some 2 value, T3, T4, T5, T6, and we sum 8 pairs of the elements. That means we sum 16, and after that we just sum them together to put them into a T. Then we do the binary reduction based on the value T instead of all the other T1 to T8. Okay, so after that we benchmark this program again. It's very easy. The only thing you need to add into your code is do the very easy serial reduction, just sum them together. Okay, so let's pick up one kernel, for example, the second one, and do the analysis to say if we solve the latency problem. Okay, let's take a look at the kernel limiter here. Now Nsight knows that my program is bounded by memory bandwidth. It's not bounded by the latency anymore. You see that we achieve more than 80% of memory controller utilization here. Even though the compute part is lower, that is because the program itself is not caused by the hardware. So we achieve a higher memory bandwidth. And take a look at the kernel latency here. So the execution dependency is very little. Synchronization is little. The most part is memory throughput. That is memory dependence. We cannot solve that problem is because the nature of this program. So if you take a look at the occupancy, occupancy looks good, looks the same because we don't change any layout, parallel layout. We just put more work within one thread. And if we take a look at the pipeline, so the pipeline is busier than before, and the load storage pipeline is above middle level. If you take a look at the memory, you will see, okay, we achieved that 176 gigabytes per second now. It's very near to the maximum memory bandwidth that it can achieve on this hardware. There are some other things you can take a look is the global memory access pattern. We don't have any issues here because our program is optimized, memory optimized, so there isn't any memory problem. The divergent execution, we have no problem. Okay, so let me show you the benchmark results. Okay, we reduced 4,000 elements on a K20 GPU. The reduction program is memory bandwidth, so the threaded memory bandwidth is 208 gigabytes per second. Let's see how each code performs. So the original code can only achieve 46 gigabytes per second. After introducing shuffle, and it gives you 1.5x speed up, and you reach 67 gigabytes per second performance. And then we add the instruction-level parallelism. Adding 2 means you calculate 2 elements before you do the reduction. Adding 16 means you calculate the 16, each thread calculates 16 elements before the reduction. Then you will see after adding 16 instruction-level parallelism, we can achieve 177 gigabytes per second memory bandwidth, and the speed up is 4.2x. So it's pretty impressive result just only by using shuffle instruction and the instruction-level parallelism. If your program will be run on Monk, and it's not possible to use the shuffle, but you can still using the instruction-level parallelism, it will still give you around 175 gigabytes per second memory bandwidth, even without the shuffle instruction. So, okay, so basically that's everything today.